Okay, hello, I'm back. Okay, our last episode ended with a cliffhanger. We were right in the middle of this problem here. We'll just kind of start it again to make sure that we get the whole thing. We wanted to find out the area between those two curves. Y equals x squared minus 2 and y equals negative x squared, right? And so it's a good idea. Remember that for this one, let me remind you that when we find the area under a curve, notice my air quote fingers there, if the function is above the x-axis, like here, right, then the area under the curve is the area between the function itself, the function graph itself, and the x-axis. So that would be the area under the curve. But if the function itself is actually below, if the function graph is underneath the x-axis, we can see here that the area under the curve is the area actually above it, between the graph and the x-axis. So when we integrate to find the area under the curve, quote unquote, we always mean the area between the function graph and the x-axis. Okay? All right, very good. So now we want to find this area here, and so it's a good idea to plot them. And you notice, oh, look at this. Here's the area, here is x squared minus 2 right there, and that's the area like under the curve, as I was just saying. Okay, then negative x squared. I'll use another color here. We'll use blue again. Well, no, we'll use, purple. That would be actually this area right here under the negative x squared curve, between the curve and the x-axis. So the area between the curve is this zone right there, right? That little kind of football-shaped zone there. That's the area between the curve. Should always go ahead and graph these when you're doing them. Make sure you're graphing them to get an idea of what you're looking at. It's the same as most of the other calculus problems we've done this year. Okay, so now we're going to subtract the upper one from the lower one. Now notice the order that I did it in. Okay, the upper one, remember, we want the area from here, which is underneath the curve, up to the x-axis. So the upper curve is actually, hope you can see, the x squared minus 2, because we're getting this area down, and the underneath is the one here. So we're going to do, even though sort of physically the negative x squared is on top, but in terms of finding the difference between them, we've got to subtract x squared minus 2 minus negative x squared, right? Okay, because the orientation is reverse from the graphs above the x-axis. So we subtract and we combine them, and we get 2x squared minus 2 after we finish simplifying the algebra problem. And we use the calculator to integrate it from -1 to +1. And Mr. Calculator, that function we worked with earlier on the curve, the integrating one, tells us that the area is negative 2.7, which makes sense because it's an area under the curve. Okay? Very good. Okay, now we're going to do a couple more examples here. Let me drag these out. Okay, so let's try number 4 here. We'll do a couple of these. Okay? Again, these are applications of finding areas under the curves, and whenever we have an actual function to work with, for now anyway, we're just going to let our calculator get the answer for us so we can kind of understand some general principles involved rather than the nitty-gritty of, which formula or procedure to use where. Okay, so we're going to use, in this here, we've got our usual thing here. We've got little f of t is equal to f primed of t, and they're going to want us to write the integral that in this form here, for the integral from a to b of f of t dt, that represents each instance below, and evaluate it using the fundamental theorem of calculus. Okay? All right, now we're going to go ahead and we're going to do probably the first two and see how that goes. Okay, so this is going to be f of t is t squared minus 3t, and I'm going to make that plus 6 there. So let's graph this to get an idea of what that looks like, okay? So this is going to be f of, on my calculator, it's going to be, let me zoom in here. Now, it's always a good idea to make sure you know what you're looking at. So that's going to be on our calculator, x squared minus 3x plus 6. Let's see what that looks like. There it is. And there, okay, so and it says from 1 to 3, so we're talking about approximately this area under the curve here, which we see is going to be positive, right? Okay, so zoom back out again. Focus. Good. Okay. Now, let's put that on the calculator here, right? From 1 to 3, I've got the limits there. Let me put the function back in, x squared minus 3x plus 6, and boom. Oh yeah, there's the area, and you can't see, but it says about 8.7. So this is supposed to be plus 6 there. So that's the integral, by the way, that we're going to write. From 1 to 3, t squared minus 3t, and there should be a plus 6 there, and then it's going to be dt, and then that works out to be about 8.7. Actually, it looks like it's 8 2/3 exactly. Okay, now this one's going to be e of t, and now just for yucks, we're going to turn this around, and we're going to do from 3 to 1. Now that's going to be this integral right here, and you're asking, well, what's the difference? Well, notice that I've reversed the limits here, right? Instead of getting area from 1 up to 3, we're going to get the area from 3 back to 1. And you'll remember that makes a difference when we talked about our properties before. So let's try this again here. So second entry, and all I'm going to do, and you should do this yourself on your calculator, okay, and I'm going to zoom back in again, okay, so that you can see this yourselves, right? And you see all I've done, it's the same integral except reverse the constants, right? And then flip, oh look, negative 8.7, right? And so remember, that's the effect if you integrate the constants from the highest to the lowest rather than lowest to highest, it gives you the opposite area, right? If the area started out positive, it's going to make it a negative. And like in the last example, if the area started out negative, reversing the constants will make the area positive. Okay? All right. So that's something that's very important. The order of these constants here these endpoints here, the limits of the integration, that makes a difference. Okay, so let's try this one. Let's put e of t in, and again, I'm going to have it. Here's e to the t from negative 1 up to 4, right? And that's going to look approximately like that. So we're going to want that area there. Let's see what happens. Okay. So I change the function and I do negative 1 up to 4, right? And I make it e to the x, and I know you can barely see that. Don't worry about it. I want you to do it on your calculator anyway. Okay? And that works out to be, so this one is, that goes there. This one goes here. This one is 54.2, rounded off. And if you see, I've just reversed the constants. And so that would work out to be, oh, and I forgot to write the integral. Oopsie. So that integral like this, negative 1 up to 4, e to the t dt. And then this one would come out to be negative 54.2 is 4 up to negative 1 of e to the t dt. So that's how we write the integrals. And I'll skip those two to make this go a little bit faster, okay, because it's the same thing. Okay? Although, check this one out. You should try that one yourself. That one turns out to be negative, and you should see why. Okay? Should check out why. All right, so that's that. Now we've got one more set of problems I want you to try, and these are just going to be practicing some more of the way of combining integrals. Okay, and here's an example here in example 5. We're going to say that we know, you're given, that when we integrate a certain function from a to b, the area comes out to be 10. If we integrate the square of that same function, f of x squared, sorry, not f of t, f of x squared from a to b, the area, that squared version of the function, if we square the function and then get the area, it turns out to be a little bit more, 14. Here's a third function here, okay, from a to b, it's g of x dx is equal to 6. And then that same function, bad handwriting here, sorry, that's supposed to be g of x quantity squared dx. And that area works out to be 10. Okay, so that's just given. So what would this be? What would we get if we combined f of x from a to b with g of x from a to b? Well, that's equal to f of x plus g of x separately, you understand. So that would be equal to 10 plus 6, which is 16. Yeah? Not 17. Okay? This one here, remember what we did about constants? There's a constant on the inside. So we're going to slide this constant to the outside, and it becomes 5 times the integral of f of x dx from a to b, right? So f of x dx, that's still equal to 10. So that's equal to 5 times 10 is equal to 50. If this were negative 5, it would slide to the outside, right? So that's equal to 50, all right? This one here, f of x squared minus g of x squared, well, from a to b, that's f of x quantity squared minus from a to b minus g of x squared separately. So that's going to be, as it turns out, 14 minus 10, which is equal to 4. Okay? So that's how that goes. This one's a little obscure. You know, what's that mean? Well, that means we're going to take, if it's a plus b, right? If those are the limits, right? Let me kind of draw in a pretend f of x here. So let's pretend that that's the graph of f of x. Well, a plus 2, what would that do? That would just take each of those limits and move them to the right 2, because we're just adding 2 on them. Okay? So which would be, so now this would be, it's an appropriate color here. Okay, let's try this color here. So here is, blue. Okay, so this is going to be, that would be a plus 2, and here would be b plus 2, and you see all that did was, it just moved the constants, those limits that we're adding, the boundaries, it moves them 2 to the right. Now, what did the function x minus 2? Remember, back to your days of function transformations, if we subtract 2 from the x, see it's inside the parentheses, if we subtract 2 from the x, that slides the entire function 2 units to the right, right? So if it's like x minus x squared versus x minus 2 squared, this was x squared and x minus 2 was 2 units to the right. Yeah? So this line here, that function f of x, that's moved 2 units to the right. Well, can you see that? What's the effect of that? Well, can you see that the area will be the same? Both the boundaries and the function ended up moving 2 units to the right. Keep saying left. This is 2 units to the right. So this area under here is equal to that area under here. So in effect, adding 2 units to the boundaries, but then subtracting 2 from each x that moves the graph to the right. Okay, both things are moved 2 units to the right. So the effect is we don't need them. They cancel each other out. So we get the same function back. This moves the boundaries 2 units to the right. This moves the graph of the function 2 units to the right. It has the same effect. The area, it's not the same position, but the area under the curve is the same. And so, oh yes, the function without it, the integration without any of that jazz is the same thing as that. Okay? And let's see, and I think that, and this says, and look at this. This is A to B. Notice I've flipped the constants like that, B to A. So since I've reversed the constants from A smaller to B larger, we're going from B larger to A smaller. That means we're going to write that as negative f of x dx from A to B. That's how that works, okay? All right, very good. Okay, so that's really enough out of me. You've got enough to get on with, I think, with the homework, which I'll be posting a little bit later today. Alrighty? But and then if there's any questions about this, don't forget, send me emails. And then what we'll do is later on, I will probably, let's see, I'm going to open up a conference for homework. I'm going to put it at 10 o'clock today, 5/6, which is Wednesday. Okay? 10 o'clock. If you have homework questions, please go ahead and ask about them. I don't know if you'll listen to this by the time 10 o'clock comes around, so I will put an announcement and an email about that, okay? Bye.